This is Dr.D Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we will discuss the location of centroid for the composite sections. The center of gravity, it can be determined by using two methods, method of moments and integration method. Even the graphical method is also useful, but it is a tedious and it takes more of time, hence generally it is not preferable. According to the method of moments, the moments created by the component of forces is always equal to the moments created by the resultant of all that forces at a given point. According to that relations we got, the x coordinate with centroid is given by xc, which is equal to sigma of mx divided by capital M, where capital M stands for the total mass of the system, or it can also be written as sigma of wx divided by w, where capital W is representing the weight of the object, small m is representing the mass of each element in which the body is divided into several parts. Similarly, yc is equal to sigma my divided by capital M. The three-dimensional object is having uniform thickness. The modified equation, it can be written as now xc is equal to sigma ax divided by capital A. Similarly, sigma yc equal to sigma ay divided by capital A. Where capital A is representing area of given object or the plane lamina, and A1, A2, A3 is representing the area of the number of parts that the object is divided. Similarly, when it is having uniform cross section, then the object is treated as linear now. In that case, the center of gravity can be determined by using graphical method, can be determined by using method of moments or by the integration method. According to this one, xc is equal to, we can write it as sigma of xdl divided by integration of dl. When we are now taking in the form of moments, it also can be written as x is equal to m1 x1 plus m2 x2 divided by m1 plus m2. Similarly, yc is equal to m1 y1 plus m2 y2 divided by m1 plus m2. And when it is in the form of area, we can written as xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2. Yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2. These equations are generally used for determination of center of gravity of composite figures, where a1, a2 is representing the area of each element or in which the object is divided. Here, find the center of gravity of the T section which is shown in figure. The object is divided just based on to give regular figures such as rectangle, square, triangle, semicircle and circular and so on. Okay, in this case, the dimensions of the given T-shaped object is given as 100 by 150 mm into 30 mm is given now. 100 mm is representing web length. Height is given total height 150 mm and the thickness of web is equal to 30 mm is given now. Hence, this object can be divided easily into two rectangular components which are represented here as A, B, H, C, and one more is E, F, G, D now. And moreover, on observations, it is found that the object is symmetrically distributed with respect to the vertical line. Hence, we can take it as that vertical line as one of the reference line. And one more reference line is which is passing through the bottom of the figure now. That is through EF and parallel to the upper surface of the wedge. Now, since it is symmetrical about the vertical line, the center of gravity or the centroid always lies on symmetrical lines. Hence, here the vertical line is treated as y-axis, hence x coordinate is equal to 0 now. Now, only we have to represent the y coordinate, that is the height now. Here, when you are taking the upper part is now treated as a first element, assume it is represented as 1. It is the second now. Now, for A1, the area is equal to 100 by 30, which is equal to 3000 mm square, which is represented here now, 100 into 30. Similarly, Y1, the Y1 is representing the centroid of the figure AB, HC. The centroid always lies at the intersection of the diagonal, or it is also now just midpoint of the width, which is given 30. That means total height is given 150 minus 15, it is equal to 135 mm. Here, Y1 is equal to 150 minus of 30 by 2, which is equal to 135 mm. For the rectangle EFGD, the area is represented as A2, which is equal to 120 by 30. It is equal to 3600 mm square. And YT is equal to, that is the position of centroid from the base, that is here now, which is the passing through point EF. It is located at midpoint of the rectangle EFGD. That is the height is given here according to figure. This height is nothing but equal to 150 minus 30, it is equal to 120. Hence, YT is equal to 120 by 2, it is equal to 60 mm here represented. This Y1 and Y2 is representing center of gravity of plane figures 1 and 2 with respect to the bottom line. So, the center of gravity of whole section is obtained according to the method of moments. YC is equal to A1 Y1 plus A2 Y2 divided by A1 plus A2, which is equal to A1 is equal to 3000 plus Y1 is equal to 135 plus A2 is equal to 3600 and Y2 is equal to 60 divided by A1 plus A2, which is equal to 3000 plus 600. On simplifications, we got 94.1 mm. That is the center of gravity. It is always represented with respect to some reference line. It lies on the middle lines, that is vertical symmetrical lines, but at a distance of 94.1 from the surface EF. That is the EF surface. This is the position of G now. We are taking the centroid of the second section, that is L section now. Since the object is not at all symmetrical about the vertical line or horizontal line, in this case, the reference lines has chosen as x-axis is representing, which is the passing through the this bottom of the figure. Okay, according to this one, it is represented as here A, B line, AB line. Here it is representing x-axis, and y-axis is treated as extreme left position, which is perpendicular to the x-axis what we selected now. So this is treated as a y-axis now. So we have to represent the coordinates of centroid with respect to the x-axis and y-axis. Now, since it is a composite figure, we have to divide this figure into symmetrical figures. It may be in the form of rectangle, square, triangle, semicircle and circle. Here it is only possible to divide it into two rectangles now. Here one is representing here A, S, G, D. I am taking E, one rectangle. The second one rectangle is representing E, F, G, Already B point is there now. Here I am representing these two rectangle sides by using hatching lines now. It is one rectangle and it is a one more rectangle. Now we have to determine the A1, that is the area of the cross section of first one, and its center of gravity, that is the x1, y1 coordinates with respect to the extreme left position, that is the y-axis, and x-axis which is passing through the bottom of the figure now. Okay, according to the condition now, A1 is equal to the area of the first figure, it is equal to 100, by the thickness is given 20, that is which is equal to 2000 meter square. Similarly, x1, that is the coordinates of centroid of first figure, it is equal to, the thickness is given 20 mm, it is in the form of rectangle, hence it is given by x1 by 2, or which is equal to 20 by 2, which is equal to 10 mm. Similarly, y1 is equal to that 100 y1 height is given 100 divided by 2, which is equal to 50 mm as shown in figure now. Similarly, for the rectangle 2 now, it is represented here as EFGH, EFGB. The area is given by, since in the bottom position AB is representing 80, but already thickness we removed, we considered in a rectangle 1, hence it now becomes 60. The center of gravity is given by AE, since with respect to the vertical we are taking, that is x2 is equal to, we can take it as AE plus EF EB divided by 2 required now. That is which is equal to 20 is given now. That is 60 divided by 2, which is equal to 40 mm. So it is given 20 plus 60 by 2, it is equal to 50 mm. Similarly, y2 is equal to, the thickness is given 20 mm by 2, which is equal to 10 mm also. Now, according to the method of moments, the centroid of the whole figure, that is with the combination of two rectangles A1 A2, is given by A1 x1 plus A2 x2 divided by A1 plus A2. Okay, according to the relations now, 2000 into 10 plus 1200 into 50 divided by 2000 plus 1200, which is equal to 25 mm. Similarly, the distance between center of gravity of the section from the bottom, that is the y coordinate, A1 y1 plus A2 y2 divided by A1 plus A2, which is equal to 2000 into x1 is equal to, that is 10 mm, that is y1 is equal to 10 mm plus 1200 into, sorry, yc is equal to A1 y1, A1 y1 is equal to 2000 into y1 is equal to 50 plus the second one is area of the cross section is equal to 16 to 20 is equal to 1200. In the middle is given 10 divided by A1 plus A2, which is equal to 2000 plus 1200, which is equal to 35 mm. If we observe, the center of gravity is somewhere here now. That is xc is equal to 25 mm, yc is equal to 35 mm. That means the center of gravity, it may lies within the objects or it may be outside the object, where that entire area of the object is assumed to be concentrated irrespective of its notations. Similarly, one more figure now. A uniform lamina shown in figure consists of a rectangle, circle and triangle. Determine the center of gravity of the lamina. All the dimensions are given in mm now. So, in this case again, Since it is treated as a regular figure now, according to the engineering mechanics, because the regular figure is nothing but only it may be triangle, rectangle, square, circle, and semicircle. Hence, it may be the combination now, but here this figure is treated as a irregular figure. For this, in order to determine the center of gravity of this figure, let us consider the line which is passing through the bottom of figure. It is treated as x-axis now. Extreme left position is treated as y-axis. Now, consider the areas first figure, second figure, and third figure. Similarly, their center of gravity x1, y1 with respect to the x-axis and y-axis what we have chosen. After determining the x coordinates of that entire lemma is given by x is equal to a1 x1 plus a2 x2 plus a3 x3 divided by a1 plus a2 plus a3. Similarly, yc is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So, first we required a1 x1 y1. So, first triangle is, first we are taking rectangle now, which is represented here now. There, the length is given 100 mm and breadth 50 mm. Hence, area of the cross section equal 100 by 50 is equal to 5000 mm square. Similarly, x1 it is equal to given total 125. That is, if I represent here now the line A, B, and C, the center of gravity that is the x1 is equal to, we can take it as AB plus BC by 2 now. That means here 25 plus 100 by 2, which is equal to 75 mm. Here we have taken here now. Similarly, y1 is equal to half of the rectangle now. That is 50 by 2, it is equal to 25 mm. Similarly, the second figure, it is in the form of semicircle. 80 is equal to, since half of the circle it is given by pi r square by 2, which is equal to 982 mm square, and xt is equal to, generally from the base it is 4r by 3 pi, but we are now taking from the other end opposite side. Hence, it is treated as 25 minus 4r by 3 pi. 25 minus 4, r is equal to 25 mm by 3, which is equal to 14.4 mm. And yt is equal to again 50 by 2, it is equal to 25 mm. Similarly, for the triangle, A3 is equal to half into base into height now. That is 50 into 50 divided by 2, which is equal to 1250. X3 is equal to, we can take it as 25 plus 50 plus 25, which is equal to 100 mm. Again, for the triangle now, where it is there now, here, xc is equal to 25 plus 50 plus 25, it is equal to 100. And y3 is equal to 50 plus again h by 3, 50 plus 50 by 3 now, which is equal to 66.7 mm. So, the distance between the center of gravity of this section and the left edge of the circular portion is given by, since it consists of 3 now, a1 x1 plus a2 x2 plus a3 x3 divided by a1 plus a2 plus a3, which is equal to 500 into 75 plus 982 into 75 plus 1250 into 100 divided by 500 plus 982 plus 1250, which is equal to, on simplification we got 71.1 mm. Similarly, the distance between center of gravity of the section and bottom face of the rectangular portion is given by a1 plus a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So, which is equal to 500 into 25 plus 982 into 25 plus 1250 into 66.7 divided by total area is equal to 500 plus 982 plus 1250. On simplification, we got 32 mm now. Okay, this is a way of locating center of gravity of the composite figure. When it is divided, we may get that parts are in the form of square, rectangle, circle, semicircle, and triangle, and so on. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.